this example of a statically indeterminate system, note that we have a wood post with two steel plates. Now just two, not all the way around, but just only two. So let's draw a view from on top, or a cross-sectional view, that we have those two steel plates covering our wood post, right? And the wood is rough cut, so its genuine dimensions are 6 inches by 6 inches, and the steel has a 1/4 inch thickness, right? And we've got a very large load of 180 kips being imposed on this, and we're asked to find the actual stresses in the wood and the steel members. Right? So from an equilibrium standpoint, if we come along and cut the cross section and draw then our free body diagram from the side, we've got this rigid cap up at the top. We have a concentric load on a concentric system, and so there's our 180 kips, and then we've got our axial force in the wood. The question then becomes, how do we want to handle the steel? And I'm going to choose to talk about the axial force in the steel as being from one plate. So that means in reality then I have to have two of the steel plates showing, right? We could have done this, since it's a symmetric situation and a concentrically applied load, we could have represented the entire steel force over here right on the longitudinal axis of the entire member. The thing is when you do that, it doesn't look like that's where the steel is at, so sometimes that's confusing to folks. We have a very simple axial equilibrium, equation of equilibrium to work with. We've got two of the steel forces plus the wood, and then minus 180 equals 0, and that of course gives us the most important equation that we get out of here on this, that the sum of the axial forces in the wood and the steel have to be equal to the applied. Right, now, in terms of displacements, note that when we say a rigid cap, that means there's no bending on the cap, and since everything is concentric, when the cap displaces, it's going to displace downwards uniformly, and note that that's going to be exactly the same displacements as happens in the wood and in the steel. So delta cap will equal delta steel will equal delta wood. That's just displacements. Now, as well, since the far end of the post is not displacing, that means that delta steel is going to equal the deformation in the steel, and delta wood will equal the deformation in the wood. Now that's shortening. That displacement would represent shortening in terms of deformation, and the force that we've shown on the free body diagram also represents compression or shortening, so therefore there's no arbitrary minus signs that we ought to put in here. All this is consistent with each other, which is the key. It's all consistent, right? And of course ultimately what that's going to tell us for our compatibility relationship is that our deformation in the steel is going to be equal to the deformation in the wood. And that's going to feed right into our basic model that says a delta of the, or any delta in the linear elastic range is going to be equal to NL over EA, or N over the axial stiffness, where K is equal to EA over L. Right, and so now let's go find out what that is. For each one, K steel will equal EA over L for the steel. And that's, well, let's see, A36 steel, if you haven't memorized what the modulus of elasticity is for steel, then you need to go look it up. That's going to be 29,000 KSI. Some people use 30. It's not as precise. It's more commonly taken as 29,000. The steel here, N steel, is for one plate. That's what we decreed all the way up here at the beginning. So the area that we use has to be consistent with that. So 1/4 inch by 6 inch, and then its length is 30 inches. And so that's going to be 29,000 times 1.5 square inches divided by 30, or 1450 kips per inch. Pretty big stiffness. 1,450 kips. That means 1.45 million pounds to get 1 inch of deformation out of those steel plates. For the wood, we'll have, well, 1.8 million psi, which is 1,800 ksi, so that we end up with common units. And then since it's a rough cut wood, that means the actual dimensions will be taken as 6 inches by 6 inches. It's also 30 inches long. Notice they don't have to be fully bonded all the way along the length, the steel and the wood. There's other reasons why we do that, but in this case they have the same displacement at the top, same displacement of 0 at the bottom because it's fixed, and that is going to, number here is going to be 2160 kips per inch. So this wood is actually stiffer as a member than what the steel member is. Right? So now we've got these stiffnesses, we can come back to our compatibility equation and we can do some mathematical work. We've got delta steel equals delta wood, and delta steel is equal to N steel over K steel, and delta wood is equal to N wood over K wood. So therefore N steel is equal to the K steel over K wood times the N wood, and that would be 1450 kips per inch over 2160 kips per inch, so those units would cancel out. And then we go and we substitute this into our equilibrium equation. Right? To save some space on the page so I can do this all one, I'm actually going to put this right up here. So 2 times 1450 over 2160 N wood plus N wood is going to be equal to 180. And therefore, N wood would be equal to 2 times 1450 divided by 2160 plus 1. Take the reciprocal times 180. And we get 76.8 kips. And that's going to mean N steel is going to be the balance of this. And then there's two of them, so 51.58, so 51.6 kips. Right? That's just the axial force in each. Now we got to get the stress. And so sigma wood and sigma steel. Let's see, sigma steel, let's do that one. That's going to be N steel over the area of the steel. That represented only one of the plates, so that's 51.6 divided by 1/4 inch and a 6 inch to get really 1.5 square inches. And that's 34.4 KSI in compression, and that is less than the yield stress of A36 steel, which is 36 KSI. It may not be less than the allowable, but that is less than the yield. So that consistency is good. It means that the steel is elastic. So that's good. That's what our model is based on. When we come over to the wood, let's see what we get there. And wood over the area of the wood, we've got 76.8 kips over 36 square inches. And I see a budding problem here. 76 divided by 36 is 2.1 KSI in compression, and our limit here for compression or the yield stress is 2 KSI. So that's greater than 2 KSI, our yield stress for the wood, assuming no buckling here, which would actually make the problem worse. That's no good. So then we're left with, well, how are we supposed to answer this? This is no good because the wood is not elastic. And how we're going to handle this is in a separate video, because we're going to have to do partially plastic or fully plastic analysis in order to figure this out.